Hello everyone, welcome to the 8th tutorial session of problem solving through programming in C. So this is the SWAYAM course which has been floated by Professor Anupam Basu from Department of CSE IIT Kharagpur, and I am Siddhant. I am one of the 3 TAs who are in charge of these tutorial sessions where we will discuss the week's concepts and solve a few questions which will help you out with the assignment problems as well as with the final exam. So in week 9 we looked at the macros and how they can be used in the code, and we also had a look at different kinds of searching and sorting algorithms such as linear search and binary search, and sorting algorithms such as insertion sort and selection sort. So we will look at a few questions concerning these concepts and we'll try to solve them in this session. Okay, so let's start. So first I have a few questions regarding macros and preprocessor directives for you. So basically macro is anything that has been defined along with the preprocessor directive for the entire code, and as you know, macros cannot be once you have created a macro, you can only destroy a macro using certain specific commands, and you cannot use the same name that you have used for a macro as a variable later on if the macro still exists. So keeping that in mind, let us solve a few questions. So let us look at the first question. So you have a macro which is A, and we have defined that using some if condition, and then we have used a define, which is actually used to define a macro, to the way that you initialize a variable using int a, int b. The same way we can define macros as define using this define keyword, and we have under this condition we are defining this macro b, and it has a value of 0. That's what we are saying. And then we have another else condition where we are defining b as not as 0 but as 1. So what do you think should be the value of b that you are printing inside the main function here? You can answer either in the chat or by unmuting yourself. So basically, okay, and why do you think it should be none? Okay, yeah, but this is an advantage of the macros, or rather this if condition particularly for the macros, that if say I have given some condition which relates to a macro called a, and a does not exist, right? So it will actually go and so that basically this statement is not an error the way that it would happen with a normal if else statement within your function, but it will simply be considered as false. The condition would simply be considered as false, and as a result we would have the else part of the statement being defined, and that means there would be a macro called b that is defined with the value of 1, and then we reach the end of the if else statement, and when we print b, it would print a value of 1. So this is the difference between a if else statement used to define macros, or rather that means if else statement as preprocessor directives, and if else a general if else statement that you would use it within the loop. so within a function. So inside the function, if you had written something like this, it would have simply given you an error, as the variable a is not really defined, right? But in the preprocessor directives, it is more flexible. So if a macro or the conditional that I'm checking using this if else and if preprocessor directive, if the macro itself does not exist, then still no error is thrown. Rather, it just considers it to be a false, the condition to be false, and in that case, if there is a else statement, then the else statement will get executed, that is the define b as 1 here. And this is exact. Now these are the three preprocessor directives which have been used here, which is if, else, and end if. So all three of these are valid preprocessor directives, and yeah, and this is the entire. So end if is required even if you don't have a else statement, that's fine, but you need to have, if you are writing a if, you need a end if to go along with it. So you can also write something like this: if a equal to 1, then some statement here, then you would have to finish it with the end if. So end if is required for the preprocessor directive, the if else statement using preprocessor directive. You need an end if to indicate that this is the end of the if else statement. Alright, if that is clear, then we can move on to the next question, which asks regarding which of the following are the preprocessor directives in C. As you can see, two of them we have already seen here, so this is a multiple correct question. So if and end if I'll just stick beforehand, because we have seen in the previous question that both of them are valid preprocessor directives in C. So what about the other two? And yeah, define as well, we have already seen define. So what does if def do? Does anyone have any ideas, any guesses? So def, as you can see, is kind of, it seems like a short form for define. So this is basically for handling special cases like this. So the same statement I can write like this: if def a, define b as 0, else define b as 1. So this is kind of not exactly the same, but here basically I am asking the preprocessor directive to check that if there is a macro called a which has been defined, it exists, then you define b as a macro b as 0. If in the condition that this macro a does not exist, then define a macro b which has the value of 1. So basically that is what I am saying by this if def statement. So if the macro exists, so this basically is what the if def statement does. So all four of these are valid preprocessor directives. Okay, so I hope the explanation or how the if def works is clear to you, and how it's different from an if, because in if we directly checked the condition. So this is a you could say more loose condition than the one we have here. So in here, in the first question, we had that if there is a macro a which exists and it has the value of 1, only then there will be a macro b which will be defined with the value of 0. But in the case that I have written here, we just have to check if there is a macro a which exists, which has a value which has been defined prior as a macro, then it just defines b as 0. It does not check whether this a has a value of 1 or whatever. It just needs to be defined. So similarly, you also have preprocessor directives for removing macros, which is undef. So it undefines the macro, it deletes, rather you can say it deletes the macro. So you can use undef for that, and there are many more preprocessor directives you can look into, which have a variety of purposes. And also we have seen a few examples before where we have defined, using the define command, we have defined macros, say func, and very rudimentary functions, for example, can be defined as this, right? Func of x, and you have this x into x say x cube, it returns x cube. So this is basically a macro which is also a function which returns you x cube, right? So the define keyword can also be used in this manner. So this is classified as a macro as well. Alright, if this is clear, then we can move ahead to the next slide. If you have any doubts, you can just write in the chat or unmute and ask. Alright, so now there is another question related to macros before we move on to the searching and sorting algorithms. So here we have defined a macro a, small a, with the value of 10, and then we are trying to print a bunch of stuff and define and initialize some variables and print them again. So what do you think should be the output for this particular code snippet? Okay, so the thing is that so a macro, once you have defined a macro with a particular name, you cannot redefine the macro as a variable. That means you cannot, this statement that I have written is basically an illegal statement, because you cannot define a variable with the same name as the macro. So if you run this code, you will get a compilation error that first you'll get this should print a value of 10, but this will give you a compilation error here because you cannot have a variable which has the same name as a macro. If you want to do this, then what you have to do is, after the printf, just here you have to put undef a. So what that will do is that it will delete the macro a, and and then you can define a variable with that name, and you can go ahead with the operation, whatever operation you want to do. Here it is just printing, so you need to have that, and only then you can get 10 and 50 as the answer. In this case, you will have a compilation error because of this statement where you have tried to define or rather initialize a variable with the same name as the macro. So the identifier cannot be the same for the macro and the variable. Okay, I hope that's clear. Alright, so there is also another command that you could use to redefine a macro. Say you want to change the instead of this, I could still write it as a macro. I mean, if you want to have 10 and 50 as the output, another statement would be one possibility would be just undefining a, which is undefining the macro. The other statement, possible statement, could be redef. So it basically redefines a as 50. So if we write this, so what this would do is it would redefine the macro a as having the value of 50. So then if you print a, you would have 10 and 50 as the output, but this is not possible. I mean, the variable a without using the undef function is not possible. Alright, so now we move into the searching algorithms. So in the classes, in the lectures, and the two kinds of search algorithms were taught. One was the linear search, where you go through each element of the entire array and you check for the key or the element that you are searching for by comparing each of the elements of the array one by one to the key. The other process is basically the binary search, where you have a sorted array, which basically means that it is either all the elements are arranged in a ascending or a descending order, and what you do is you divide the array in half and you check if the key exists in the lower half or the upper half. Now if it exists in the upper half, you again divide the upper half and you check if it is present in the first 1/4 or second 1/4. Now you keep on doing this until you reach you get the key, or you find out that the key does not exist in the array. So that is why it's called binary search, because it always divides the array or the sub array into halves, and then it goes on checking. So that is why it's called the binary search. So here what we do is we have an array and the key is 34, and so the question asks that what are the mid values, that is the corresponding array elements, generated in the first and second iterations of the binary search. Alright, so let's see. So let me first write down the array. As you can see, the array is in a sorted form. So I'll just rewrite this first, and then we can start doing the binary search. So you can see how many elements does this array have. So 3, 3, 6 and 3, 9. So basically it has 9 elements, right? So the fifth element is the central element. So 85 is the central element, that is the half of the array. So 4 elements above this, 4 elements below this. So now the first mid value that we get from this array is the first time. That means the first time that we divide the array, what happens? So the value that we get is 85. That is what we check our key against. So we check if the key is equal to this particular element, but it's not. The key is 34 and we have 85. So in the first iteration, however, we find out that the key is lower than this particular value. So the key is lower than 85, right? So that means, as it is a sorted array, the whatever key, if it at all exists in the array, it should exist before this 85, right? So for our case, the first value was 85, so I just marked that. Now we are concerned only with the part above this array, because the key was found to be lower than 85. So in the second step, what happens? So we are concerned only with this sub array. So now we look at 12, 34, 47, 62, 85, right? Now we have again 5 elements. We go for the middle element, which is 47. Or I mean, if you don't consider 85, then your middle element would be either one of 34 or 47, okay? Because you found out that it's less than 85. So if it is less than 85, then you don't need to consider 85 as such. It's not required. Okay, so let's consider that only the array above it, that is 12, 34, 47, 62. These are the 4 elements we have, and we can take either, because it's an even number, so we can take either the upper value or the lower value as the middle element. There is no middle element as such, so there are 2 possibilities of the middle element. Now you can take either one of them and check. So here, according to the answer that is given here, so it can be either 34, it can be either 34 or 47, right? The second mid value that we get. So here, as you see, we have 34 in the option and we had 85 for the first one, so the answer should be option B. Okay, let me, so this is 34, this is 47 and 62. Say I take this as the center element, I get the key, I'm satisfied. If you take the other way, so you have this, you take this as the center element, so what happens in that case? You check the key is actually lower than this, so you have to be concerned only with this, so it has to go to a third iteration. So this was the first iteration, this is the second iteration, right? And then you go to the third iteration, which is just 12 and 34, and you take whichever, again it's a conundrum, so you can take whichever you want. So this is the third iteration, and here you will find that the key is, you have found the key. So yes, the binary search is successful in finding the element, that is the key, inside the array. So do you get how to do binary search now? I think some of you have already answered B. Yeah. Okay, is there any doubt regarding the binary search? Okay, so what happens here, I just write, you can see it is a sorted array. I write down the array. Now what I do is, I need to find whether this key, which is 34, exists in the array. Now looking at the array, I straight away go to the middle element. It's an array of 9 elements. I go to the middle element, which is 85 in the array. So this is the first iteration I'm talking about. So I look at the middle element, which is 85, which is the first mid value that we get in the first iteration, which is 85, right? Now I check if the key is greater than or lower than or equal to 85. Now I found here that the key is actually is actually lesser than 85. So that means the key has to be within the elements which precede 85, because the array is sorted, and we know that the array is sorted. So the key has to be within this range, right? So that is now the sub array that we will be considering for the second iteration. So we consider 12, 34, 47, 62, so all the elements before 85, we just consider that. And here, as you can see, it is a sub array of 4 elements. So if I talk about the middle element, it can be either the second or the third element. But here, as you can see, among the options, we have the second element as the option, which is 34, which can be a possible key, which can be a possible mid value. In the off chance that you took 47 as the mid value, you would again find that the key is lesser than 47. So the key has to, if the key exists in the array, it has to exist before 47, right? So you take the elements that is preceding 47, and you have in the third iteration, you go to the third iteration, you have 12 and 34, and you take the key as 34, you get the key, right? You compare the key with 34, and you get that yes, it exists in the array. So however, for this question, as far as this question is concerned, because there are two different ways that you could actually take the mid values for the second iteration, and it has asked what are the mid value for the first and the second iteration. For the first iteration, it's pretty clear that it's 85, but for the second iteration, it could be 34 or 47, but 34 is the only one that is there in the options. So that is what will be the answer here. So option B. Yeah, I mean, the binary search is a pretty common thing. You can just find out the codes on the internet. I mean, it's pretty straightforward. You can very easily find the codes, but you should try to write it by yourself, because that is one of the assignment questions, as far as I remember. So you should try to do it by yourself first, until you if you understand the concept, then it should be fine. It should be possible for you to write the code, I hope. Is the concept of binary search clear to everyone?
Yes, sir.
Okay. Okay, then we'll move on to the next question. So this is a question that probably we have already discussed, kind of. So when is the binary search best applied to an array? So when would you think about using binary search in an array? So this is a theoretical question. I think you can answer this. Right. So when the array is sorted, only then you can use binary search, because as you saw in the previous question, that we are assuming that if the key is greater than the middle element, then we go to the second half of the array, or if the key is lesser than the middle element, we go to the first half. So that is only possible only when your entire array is sorted, and you know for sure that if my key is, say, the array is sorted in ascending, and you check the key with the middle value and you find out that the key is lesser, so you can say for sure that yes, my element, if it exists in the array, then it is in the first half of the array, not in the second half, because the array is sorted in the ascending order. So it is only possible to use binary search when the array is sorted either in the ascending or descending order. But that is a very important requirement for the binary search algorithm. Alright, so that is something to keep in mind whenever you're using binary search. Now the second question that I have is regarding insertion sort, and here through this question I'll also explain how insertion sort works. So we have an array which is 83594, so this is our array, and we need to sort it in ascending order. So the question asks, what is the correct order in which the insertion sort works? So alright, so can you try to answer that? I'll give you some time, and then we'll discuss. Yes, I'll explain it in some time. I'm just giving some time for those who are familiar with insertion sort to try and answer this question by themselves. Then I'll explain. Okay. So this is our array, which is 83594. All right. So what insertion sort will do is, so we'll take this as the key. Okay, the second element as the key, and we need to sort it in ascending order. So we'll take this as the key, we compare it to all the elements before it. So we compare this with this, and we find that this is actually the key that we have is actually lower than the element before it, so we swap them. So this is the first step, and after the first step, the array becomes something like this: 38594. Okay, so then what is the next step? In the second step, we take this as the key, that is the next element. So this was the element with index 1, that was the key. Now we take the element with index 2 as the key, and we compare it with this, and we find out that the key is lesser than this, so we swap. right? So we get this. Now we compare this 5 with 3. So this is still the key. We compare it this way, but we don't find that it's lower, so nothing, no change there. So this is step 2, both of this together. Then we have, in the next step, what we do, we have this, we take this as the key, that is the index 3 as the key, and we compare it to the one above it. Now we find that it's not really lower than that, the key is not lower than the element before it, so we don't move anything, right? Then in the next step, what we do is we take this as the key, and we compare it to the previous element, right? And we find out that it's lower, and we keep swapping the elements until we reach this. So basically our first step is, after the first step, it's 38594, which is this and this, okay. Then in the next step we reach 35894. So 35894, this so this is eliminated, so definitely not option C or option D. So the answer will be A or B. So in the next step, it will be we'll check for 9, but we find that there is no change with 9. So it's just the same, right? We get the same one, that is 35894. So no need to rewrite that. Next we switch between 4 and 9, right? Then we switch between, okay, let me write the sub steps of this particular step. Let me write it a bit properly. So we have 35894, and this is the key. We check with this, exchange with this, we get 35849. This is still the key. We check with this, exchange with this, we have 35489. This is still the key. We check with this, exchange with this, so 34589. So you can see that this is the order that it progresses in. So you have 35849, that is this, right? Then you have 35489, that is this, and the final one, when it is completely sorted, 34589, that is this. So option B is the correct answer. So are you able to understand how insertion sort works?
Yes, sir.
Okay. Alright, then we can move on to the next question. So right, okay. So what is the recurrence relation for the linear search recursive algorithm? Okay. So in linear search, if I can make you remember that, let's say we have this some, right, something like this, say any array, we have a key which is say 4. Let's say our key is 4. So we check 4 with 8, 4 with 5, 4 with 4. We find it good. So what if you want to write a recursive algorithm for the linear search, so how would you write the recursive formula? What should be the recursive formula for the linear search? So what do? You check with the first element, and then you, if it is false, if the key does not match with the first element, you pass the rest of the elements to the first recursive function, right? Now the first recursion, in the first recursion it checks that whether the key is equal to the first element, that is 5. Okay, let me write this a bit more properly. So say you have 85496 and the key is say 4. Now this is my first recursive, the first time the function is called, I check 4 with 8 not matching. So what I do is I send this into the first recursive loop or first recursion. So now I have this array and I check this key, which is 4, with the first element, still not matching. So I send the rest to the second recursion, right? So now I have this, so I check the key against this, found it, so recursion stopped. Okay, so basically what are you doing? So here you have say 5 elements, you're checking with the first element, passing 4 of the elements, the rest 4 elements. Here you have 4 elements, you're checking, if it is not matching, passing the rest 3 elements. Here 3 elements, you're checking, if it did not match, you would have passed the rest 2 elements. So basically it's kind of a n-1 relation, because when the number of variables or the number of elements that a certain recursive function handles, and the one that it passes to the number of elements that it passes to the next recursion differs by only one element. So I can write this as t of n-1 plus some constant. You can ignore that constant for the time being. So it should be option C. So this is how the recursion should exactly work, or rather that should be the formula for the recursion. Is that clear?
Yes, sir.
Okay. Now then we can have a look at the next question, which is again insertion sort. So okay, I can explain that again. So here we had a linear search algorithm. So in linear search, what you do is you go through each of the elements, you compare your key with each of the elements until you find a match. So let's say this is my array and I have this key, say it is 4. So I compare the key with the first element. Okay, now I find that it's not matching. The key is not equal to the first element that I have. I pass it to the, and then I have to recursively do this, because that is what it's saying, that it needs to be recursive algorithm. So what I do is I send the rest of the elements, so n-1 elements, again to the same function. Okay, so I send n-1 elements to the same function. So what n-1 elements is in the rest of the elements, right? Because the first element did not match, I don't need to check with that again. I just need to check with the rest of the elements, that is the elements after the first element. So I just send this remaining 4 elements to the same function again, and what the function does only one thing: it checks against the first element. It checks the key against the first element. Now it checks the key, that is 4, against the first element here. So again we found out that it's not matching. So what do? We again send the rest of the elements to the same function. So we send 4, 9 and 6, which is the remaining 3 elements, to the same function. Now here it found out, say your key was 6. So what would have happened? So it had 4, 9 and 6. It would have checked with this. It couldn't find that the key matched with the first element. No, it did not match. So it would have sent this again to the same function. Now what would have happened? So 9 and 6 is your new array. So you check again the 6 against the first element, not matching. You send the last element, that is the remaining element here, and you check with the key, right? And here it is matching, right? So basically what are you doing here? You are passing say n elements has come to your function has accepted n elements. What you are doing is you are again recursively passing n minus 1 elements. In case you have not found the key so far, you pass the remaining n minus 1 elements again to the same function. That is, you are recursively passing n minus 1 elements. So that is what this t of n minus 1 says. That means if you have received n elements, you are passing n minus 1 elements again to the recursion. Okay, and that is what we are doing here. We had 5 elements the first time the function was called. We are passing, because we have not found the key, we are passing 4 elements again to the same function. In the next time again we did not find the key, so we send the remaining 3 elements to the same function, and so on until you find the key. Is that clear now? Right. So now we can have a look at the insertion sort. That again, and here it says what happens after the third pass of the insertion sort. Okay, so we have 10, 4, 7, 23, 67, 12 and 5. Alright, so now what will be the resultant array A after the third pass of insertion sort? So in the first pass, you know that we consider 4 as the key. We compare, we swap, so that is 4, 10, 7, 23, 67, 12 and 5, right? Now in the second one, we take 7 as the key and we compare and swap 4, 7, 10, 23, 67, 12 and 5. Second pass. The third pass, we have, so this was index 1, index 2, so we need index 3. This will be our key, and we will check. No change because the key is greater. So this is what after the third pass our answer should be, which is 4. So this is the first iteration, second iteration, third iteration, and that is what here it means by pass. I mean the same thing as iteration. So this is what we will have after the third iteration, that is 4, 7, 10, 23, 67, 12 and 5, which is option B. Is that clear?
Yes, sir.
Okay. Alright, so we can have a look at the next question then. So which of the following will give us a worst case time complexity for selection sort, to sort an array in ascending order? Alright, so before that I can probably explain to you how this selection sort works. So it will be, I can explain to you with a short array. That is, say I have this array which is 8, 5, 4, 9 and 6. So I'm just writing this for selection sort. Okay, so what happens here is that you take the first element and you compare it with all the elements, find out the minimum. You find out the minimum element. How? You compare the first element with the second. Now you keep on, so you need to arrange it in say ascending order. Okay, that is what you need to do. Say I want to check it and do it in ascending order. Okay, then you take 8, that is the first element here, as consider that as the minimum. Check with the second one and keep on checking until you find the minimum element. Okay, so here we found out that 4 is the minimum element in the first iteration. So this is the first iteration. We found that 4 is actually the minimum element, so we swap this two. So after the first iteration you will have 4, 5, 8, 9, 6. Alright, now you will take the second one, repeat it again, check, assume that the second element is the minimum one, and then compare it with the rest of the elements to check if it is actually the minimum. You found out the minimum, and here the minimum is actually the second element, though, so you no swapping. Alright, so this is the second iteration. Okay, then you go to the third one. So you say that the third element is the minimum. You check with the remaining elements. Okay, you check with the remaining elements. You found out that no, 6 is actually the minimum, so you swap these two elements, and this is the third iteration. And by swapping these two elements, you get 4, 5, 6, 9 and 8, right? Then you take this element, assume it as the minimum, and check with the remaining, but you found out that no, 8 is the minimum, so just swap it. So this is the fourth iteration, and you'll have 4, 5, 6, 8, 9, which is basically the sorted array, right? So this is how selection sort works. Is that clear? So this is a very small example of how selection sort works. Yeah, okay, so keeping this in mind, let us check what will give us the worst case time complexity for selection sort to sort an array in ascending order. Alright, option C. Okay,
B would be the answer because of it is in descending order.
right. So the worst case complexity is basically for any sorting algorithm is when the array is exactly in the opposite order that you want it to be. So here we want it to be in ascending order for this sorting, but in this case the array is in descending order. So it would take the maximum number of iterations or maximum number of operations to actually bring this to ascending order sorting. So that is why this would give you the worst time complexity, because there are the total number of operations required for this particular array would be the highest, because everything is in the opposite, completely or exactly the opposite sequence of what you want it to be. So you would have to do the maximum number of steps possible to achieve ascending sorted array here. So the option will be answer B. In the option C, however, you can see that one element is actually moved here and there, that is this element 4, which is not in order. So the number of, if you count the number of operations required for this, for the third, for this one, it will still be lesser than the one required for option B. Not very much lesser, but somewhat lesser. It will be differing by a few operations, right? So the question asks that which will give us the worst case time complexity. So that will be only the option 2, not 3, because the number of operations, although there will be no magnitude change, I mean no order of magnitude change in the number of operations, but it will vary by a few operations. So the second one is actually the worst thing that you could probably give it to for sorting. Okay, is that clear? And of course the other case is the best case complexity. The best case complexity is when you already have a ascending, in this case you need to sort it in ascending order and the array is already in ascending order. So that is the best case complexity that could happen. I mean, if the array is already sorted, you don't really, you just have to do a single pass, you're done. So what does a single pass of selection sort need? I mean, depending on that is how we calculate that, the best case time complexity, that is when the array is already sorted the way that you want to, how many iterations would this particular sorting algorithm run for. So that is your best case complexity. Okay, if it's clear what is the worst case and the best case time complexity, then we can probably go to the next question, which asks that when is a certain sorting algorithm or sorting technique called stable? also, apart from a best and worst case time complexity, there is also something called a average case time complexity. So okay, so I'll just write it down. So worst case time is when, say, you want to sort in ascending order, right? You want to sort the array in ascending order and array is in descending order. So this is when you will get the worst case time complexity. The best case time complexity you would get when the array is in ascending order. Why? When I say worst case time complexity, I mean it most number of operations required. And when I say best case complexity, I would say least number of operations required. Okay, that's what it means by best case and worst case. Now there is also average case complexity, which basically means that if the array is partially sorted or anything in between, what would on average be the time complexity of your system, that is how many operations would it normally take or usually take if the array is not in ascending or in descending, somewhere in between. So that is your average case time complexity. Okay, so in this example, in this question, the second, that is the Roman numeral 2, is the case where it is completely in a descending order and you want to sort it into ascending order, so it has definitely the worst case time complexity. So why option 3 has been discarded here is because it would be something which comes as average time complexity, because it is not exactly in descending order. So the number of operations, although it wouldn't be significantly different from option 2, in case of selection sort, if it had been insertion sort, it would probably have been a bit more apparent, but in selection sort the number of operations wouldn't be significantly different for the case 3 compared to case 2, but still there will be a few differences in operation. So the option 3 will require a few less operations to happen than the case 2. So the worst case time complexity here would be only the option 2, that is B here. Is that clear? The code is running in, yeah, I mean, until actually this time complexity is something that you cannot observe if you don't have a huge array. If you have a small array, you won't be, if you run the code on the system, you won't be able to see the effect of the time complexity. But if you calculate the number of operations manually, the number of operations that has to happen for the sorting to take place, you will find out that for the case 2 here you need to do more operations like conditional checking and swapping compared to case 3. So that is why we say it has the worst time complexity. But if you want to practically see it, that there is a difference in time, then you have to pass a huge array into for the sorting. Otherwise you won't be able to see the difference in that, because the computers, they can really these days the computers with 64-bit processors and so on, they are pretty capable of handling this. These are just pocket change to them, this kind of arrays. So you cannot see the difference in time if you just run these arrays, but if you count the number of operations, you will see the difference. Is that clear? Yeah. Okay, so what makes a sorting technique stable? So I'll just go ahead and say that if it maintains the relative order of occurrence of non-distinct elements. So what does that mean? So say you have an array 8 5 2 9 6 2 3. Okay, now you have this array, you sent it for sorting into ascending or descending, whatever. Now I am just classifying this to A and to B for my own understanding, because there are two 2's in this array. Okay, so if the array gives, after the sorting, say I sort it into descending order, after the sorting, if it gives me something like this, just a moment. So after sorting, if it gives me something like this, 6 5 3 to A to B, okay, now if it gives me something like this, then it is called stable. This is unstable, because you see this and this are non-distinct elements. These are non-distinct elements, right? Because they are the same value. If my sorting algorithm doesn't change the relative order of the non-distinct elements, that is, still this 2A occurs first and then 2B, then yeah, it's stable. And if it changes the order during its sorting operations and checking and swapping operations and whatever, if it changes the relative positions of this, then it is called unstable. Is that clear? When we call algorithms to be stable or unstable. So insertion sort is a stable algorithm, and selection sort, the classical one, is unstable, but with a few minor changes you can make it stable. So yeah. All right, so yes, do you have any questions? You can go ahead and ask.
Sir, I couldn't understand. Please explain again, sir.
Okay, the stability. Okay, okay, a sorting algorithm, you can see that I have taken this array which is unsorted and I want to sort it into descending order. Now you see that I have two number of values which are the same, which is that is why I have written just a 2A and 2B in order to distinguish them. Now say after the sorting, your sorting algorithm, after the sorting you get an array like this, that is 9 8 6 5 3, then this 2A and 2B. So in that case I would say that the sorting algorithm is stable. Why? Because these two are the non-distinct elements, because they are the same, they have the same value, so they are non-distinct. So if the sorting algorithm preserves the order in which they had occurred initially, so initially this was the A occurred first and then this B occurred, right? So if the same kind of ordering is observed after the sorting has been done, say here still the A is before the B, that means the relative order has not been changed. The relative order of occurrence is not changed in the algorithm. The algorithm doesn't change the relative order of occurrence. So in that case I'll say that the sorting algorithm is stable. Now if it had changed the order of occurrence of this non-distinct elements, that is, now the B had occurred earlier than A, even if the values are actually the same, in that case I would say that this sorting algorithm is unstable. Is that clear?
Yes, sir. Thank you, sir.
Yeah, okay. All right, so let's look at the next question. Oh, there's right. So what is the best case complexity of ordered linear search and worst case complexity of selection sort? Sorry, it's asking about selection sort. Okay, so So what is the best case complexity of ordered linear search and worst case complexity of selection sort respectively? So we are looking at this question first. I think this should be fairly straightforward to answer. The best case complexity is order of 1. That is, when would it be the best? So in linear search you start searching, it is saying ordered linear search, right? So you search, you start from the first element, and the best case complexity is the first element itself is the key. So you just have to check once, you're done. If you check once, you're done. So it's order of 1. The best case time complexity is order of 1. Now the worst case time complexity of selection sort, we saw it earlier. We didn't see the order exactly, but selection sort has a worst case time complexity of n square. So order of n square, I'll derive how it exactly has a worst case time complexity of n square. I will derive that, yeah, I mean, so option A is our answer. So hopefully right now you can understand at least why the base case complexity of ordered linear search is order of 1. Is that at least clear to you, why it is order of 1? Okay, I think there are no doubts then. The worst case of selection sort, I'll derive that by the end of the tutorial session. Alright, so the next question that we have here is regarding the linear search algorithm again. Now, when is the average case of the linear search algorithm? So we talked about the best case, the worst case. So what would be an average case? I have already told the answer in the previous slide. So what is exactly average case time complexity? So anything between the best and the worst is the average case time complexity. So that means the key that you are searching for, it's not at the first, not at the last, but somewhere in between. So it's somewhere in the middle of the array. So yeah, so that would be your average time complexity, right? Somewhere in between, not the first element, not the last element, somewhere in between. Yeah, do you have any question?
Sir, 1 minute.
Yeah.
I'm Yashwant sir. Actually, you say that the complexity of linear search is O of 1, right? Right?
Yeah.
How can you say that's O of n square? So there are so many searching and sorting algorithms. So how can you predict that O of n square is the is related to the selection sort? In binary search is one of the sorting algorithm, yeah.
Binary search is a searching algorithm. Selection sort is a sorting algorithm. But I say that the worst case time complexity of selection sort is O of n square, and I can prove that to you, and I will prove that to you by the end of the tutorial session. So separately I'll do that. Yeah. Okay. Okay, so let's go to the next question. So we have, again, it's a question on insertion sort. So we have an array which is 51, 14, 23, 9, 24, and we apply insertion sort to sort this array, and say the cost of sorting of each sort, that is each iteration, is 1 rupee, that is each pass that we talked about earlier. So each pass is 1 rupee, the sorting cost. So what is the total cost of the insertion sort for sorting the entire array? Let's say in ascending order. So basically it asks, the question is asking that how many okay, we'll see. So basically the question is asking that how many passes of the insertion sort is required to sort the array into the cost that they have mentioned, that is 1 rupee. So basically how many passes are required. So let us check that. So we have this array. So as I have told earlier, this is the key. So I have told earlier this is the key and it gets swapped. This is first iteration, right? It gets swapped. So you have 14, 51, 23, 9 and 24. Then this, check, swap. This is second iteration. So 14, 23, 51, 9 and 24. Then this is the key. Compare, swap. This is the third iteration. So 14, 20, oh sorry, not just here swap. It swaps a lot. So it swaps here, then oh my god, 14, 23, 51. Yeah, this is, then it goes here, goes here, goes here, or rather let me write it as this, it will be easier to explain. This was 23, right? 23, 51, 9. Alright, we have this as the key. It gets swapped with this, and this gets here, this gets here, this gets here. Okay, so this is the third iteration, and after this it becomes 9, 14, 23, 51, 24. 24 is now the key. It gets swapped here, it comes here. So this is the fourth iteration, and you have 9, 4, 23, 24, 51. Now it's sorted. So you don't need to take, so you have 4 indices that you need to take as a key. That means you need 4 passes of the entire array. So each of this has the cost of 1 rupee. So your total number of iterations required was 4. So the cost associated will be 4. Is that clear?
Yes, sir.
Okay. All right. So let us look at the next question, which is asking what kind of algorithm is the linear search algorithm. So yes, we have already answered correctly. So the linear search algorithm is actually a brute force algorithm. That means it does not care about it goes through all the elements, right? A brute force algorithm, it goes through all elements and does not try to do anything clever. Basically it just steamrolls through all the elements in order to get its work done. It does not use any clever tricks that the other search algorithms and so on use. Now dynamic programming is something completely different. Probably we'll see it by the end of the course. But what about the greedy algorithm and the divide and conquer algorithm, right? So the greedy algorithm is basically something that takes the most optimal action at every point, most optimal value rather at every step. It's greedy basically. It wants the best all the time. So it takes the best, that is the optimal value at every step. So that is what a greedy algorithm is. So here example is selection sort. Why? If you remember now that selection sort takes the minimum, depending on whether you are doing ascending or descending, it takes the minimum or the maximum value. It finds out the minimum or maximum value at every time step, or sorry, not time step, at every step of the iteration or every iteration. It finds out the minimum and or the maximum value of the array or the sub array. So that means it at every iteration it wants to find the best or the most optimal value. So that is why selection sort is a greedy algorithm. Now what about the divide and conquer algorithm? So divide and conquer algorithm, it's pretty straightforward to understand, that it divides the entire array into smaller parts and then it does the sorting on them, and again it conquers over the array, it merges the array back, it conquers, it does the sorting thing in respect to the sort. But in overall, it is basically you are dividing and simplifying the problem. So it divides the array, simplifies the problem, solves the problem. So examples of this would be merge sort. So merge sort, what it does, I'll just explain the theory because the practical is a bit more involved. So merge sort, if you have a large array, it will keep dividing the array until it gets each element out, and then it starts comparing and merging the array in ascending or descending, whichever you wanted, and it will again merge back while comparing and swapping in, and finally it will get the completely sorted array. So that is how merge sort works, and it is a divide and conquer because it divides the entire array into smaller and smaller divisions, which makes it easier to sort, and then it merges it back. Okay, so yeah, if all of that is kind of the theory, more or less, different kinds of algorithm. Any questions? Alright, if there are none, then we'll just go and do the derivation. Now I'll answer your question as to what is the best case and worst case complexity of. So here when I say complexity, I'm just referring to time complexity of the classical selection sort. So we'll look at the classical selection sorts best and worst case time complexity, but I'll tell you this beforehand that for the selection sort, for the classical selection sort, the best and worst case time complexity is n square. For both, that is the best, that is the worst. I mean, selection sort, because it's a greedy algorithm, because it insists on taking the minimum or the maximum, that is the most optimal step at every iteration. That is why it takes more number of operations to sort the array, even if the array is priorly sorted. Okay. Now we need the best way to calculate this kind of stuff, or to derive this kind of stuff, is to take an example. So I'll just take example of this array 51, 14, 23, 9 and 24. So we'll do best here and worst here. Okay, so my array is 51, 14, 23, 9, 24. So this is my array, and okay, I mean these are my elements. So the worst case and the best case, what would they be? So say I'm talking about ascending order. You can do the same for the descending order as well. So say my best case, so my best case for ascending order would be what? 9, 14, 23, 24 and 51. And for the worst case, it would be the complete opposite, right? That is, everything would be in descending, so it would be this, right? Now what does selection sort do? It takes the first element, right? It compares with the rest of the elements. So how many comparisons here? So 9 would be compared to 14, 23, 24, 51. So you have 4 conditional statements. Alright, and it found that it's fine. There is no swapping that is required, so no swaps. Alright, it's the minimum. It found that 9 is the minimum, so good with us. Now it goes to the next iteration. In the next iteration, what it will do? So it will check 14. It will assume 14 as the minimum, and it will check with 23, 24 and 51. So 3 conditional checkings here. Okay, now it still found that it's the minimum. Okay, cool, move on to the next. So 9, 14, 23, 24, 51. So it takes 23 now, assumes minimum, and compares with the remaining elements. So 2 condition checkings, right? No swappings though. Then again what it does is it takes 24 to be the minimum, checks with the remaining element, one condition checking, no swapping, and then it finds sorted, array is sorted now. So total number of operations was 4 plus 3 plus 2 plus 1, right? Or rather, if I say for n elements, so say there were n elements, so here there were 5 elements, so we had 4 conditional checking for the first iteration. So for n elements we'll have n minus 1 plus n minus 2 plus n minus 3 all the way up till 1, which basically is n into n minus 1 by 2. This is the total number of operations, right? So this basically means order of n square, right? Because n into n minus 1, so it's order of n square. So can you try to do the worst case complexity? Okay, so in the worst case complexity, what happens? It takes 51, considers the minimum, then it does what? 4 conditional checking here and 1 swapping, right? Because it finds 9 is the minimum, so it swaps, right? So I'm representing the actual minimum by this circle and the assumed minimum. Yeah, anyway I'll be explaining it again here so you can understand. So okay. Alright, so we assume 51 to be the minimum, and then we keep on comparing with the other elements, that is the remaining elements, all the elements below it, and find out the actual minimum. Now once we found out the actual minimum, we swap both the things. So here how many conditional checking will be there? We will compare 51 with 24, we will find 24 is lower, then we will compare 24 to 23, find 23 is lower, compare 23 to 14, find 14 is lower, then compare 14 to 9, find 9 is lower. So 4 comparisons and then 1 swapping, that is between 51 and 9. So in my next iteration my array will be something like this, right? Now it will go for the second element, it will assume 24 to be the minimum, and then it will check with the rest of the elements. It will check 24 with 23, find 23 is lower, then it will check 23 with 14 and find 14 is lower, and then it will check 14 with 51, find 14 is lower. So this, it will go here and will swap, right? So 3 conditional checking and 1 swap, right? Now after this the arrays look something like this: 23, 24, 51. To us the array looks sorted, but the sorting won't stop here. The sorting will go ahead and take 23 as the minimum. It will compare it with the next elements, that is it will compare with 24 and then with 51. So you will have 2 conditionals, 0 swap. Okay, now in the next step again it takes 24 as the minimum, assumes it as the minimum, and then it compares with 51, finds out minimum, so 1 condition, right? 0 swap, and then it knows that it's sorted. So so here how many operations do we have? We have 4 plus 3 plus 2 and some swaps, some number of swaps, right, for 5 elements array. So total number of operations, if I have to write, so the swaps are lower number of anyway, in any of the cases there can be a maximum of 1 swap. Alright, so we'll just add a max of n, so that's fine. So the main number of operations is the conditional checking in the classical selection sort. So the total number of operations here, it was 4 plus 3 plus 2 plus 1 in an array of 5 elements. So if it is an array of n elements, you will have n minus 1 plus n minus 2 plus n minus 3 all the way up till 1, which is again n into n minus 1 by 2. now you can add some value which is less than or equal to n will be added with this, but doesn't matter because your overall order will still be n square. Do you understand now why selection sort has a worst case and best case time complexity of order of n square? Someone had asked that question earlier, I guess. Is it clear?
Yes, sir.
Okay. And to the one who couldn't understand and messaged, Wasavi, are you clear now how to calculate the best and worst case time complexity and why it came out to be order of n? The same thing that I explained for the worst, you can apply the same thing to the best one and do it. Alright, so we saw that for classical selection sort, the order that is the time complexity for the best and the worst case is order of n square. So the average time complexity is also order of n square. Okay. Alright, now we'll do the same but for the insertion sort. Okay, I'll just rewrite the array, which is 51, 14, 9, 23, 24. So these are the elements anyway. So we will do a ascending order again. Okay, and we'll do the best and the worst. Alright, now the best case, let us just write the best case down first. 51. Okay, now we will take this as the key. So this is our key, right? We compare it to the elements above it, and so we will do one conditional checking here, no swapping, right? No swaps. One conditional checking, no swaps. In the next iteration, we will take 23 as the key. We will check with the elements above it, so two condition checking, but no swaps because none found to be they are all the elements that we checked with are lower than the key, right? Then we go with 24 as the key, check with the previous elements, three conditional checkings, no swaps, right? Alright, okay, just a moment. Okay, I think I messed up somewhere. Oh, right, okay, I see. Let's do the worst case first, because it helps understanding the algorithm properly. Then we'll do the best case. So we have 51, 24, 23, 14, 9. This is our array. We'll go for the key. The second element is the key. We compare it to the elements before it, and we swap. So one conditional, one swap. Then we have 24, 51, 23, 14 and 9. So we take this as the element and we have to swap it. So we swap this to this. Actually the swapping will be in this manner, that 23 and 51 will be swapped, then again 23 and 24 will be swapped. But for ease I'm just writing it like this to show the number of swaps and the conditional checking. So two condition checking and two swaps. Alright, now what will the array be after that? So this will be the array. Now you have this as the key. Then what you do is you compare it with the three conditional, you have three conditional checkings before it, and you swap it accordingly. So you will have the swapping take place like this. So three conditional checkings and three swaps here, right? So you will have 14, 23, 24, 51 and 9. Then you have the last element as the key, and you check with the previous 4 elements and swap it accordingly. So you will have some swaps like, okay, and there was one more. So you had this is 24, right? Oh no, this is 14, this is 23, 24, 9. So this came here, this came here, this came here, and this came here. So 4 conditionals, 4 swaps. So if you calculate the total number of operations for a array of 5 elements, you have twice of 4 plus 3 plus 2 plus 1, or for a array of n elements, you have 2 into n minus 1 plus n minus 2 up till 1, which is basically n into n minus 1, right? That means order of n square. That is the worst case time complexity for the insertion sort. Is that clear? Is that clear? How does anyone have any doubts? Alright, so next we go to the best case, which is basically 9, 14, 23, 24, 51. We have the array like this, and we need to do the insertion sort. Alright, so the first step is taking the key, which is the index 1 element, which is 14 here, and okay, now right, so we check with this. I mean, sorry, I shouldn't have drawn this arrow. We check with this, and okay, before that I can tell you this, that in a case where the first element, that is the element just before it, is not lower than, I'm doing it in ascending. So let's say I have a key and I'm checking it with the element which is just above it. Now if the element just above it is greater than this, then it's fine, then there will be some swapping, there is some unsorted thing there. But if there is if you are checking the key against the element just above it and you saw that it is actually lower than the key, that means you are fine. So you don't need to do any more checkings in that case in insertion sort, because the insertion sort works in the way, in each of these cases, you see, once it has started sorting, there is always the array, the part of the array, the sub array which is above the key, is always in a sorted form. Now if you check the key with the element just above it and you found that the key is greater than that element, that means it would be greater than the rest of the elements. Okay, so you the insertion sort is written in such a way that you check it with the one with the element above it. If there is some swapping, then you will do the swap, you will check again. Okay, now that is what will happen here. You will have one condition checking here, you will have one condition checking between 9 and 14, okay, and 0 swaps, because no swaps are required. So you will just do a condition checking between 9 and 14. Okay, you found out it's not I mean the key is greater than the element, so nothing to be done. So in the next step, you take 23, you check it with 14. Now you saw that this 14 is actually lower than our key, which is 23. So you don't need to check with the elements before it, because they would definitely be lower than this. So there will be one condition checking, which will be between 23 and 14, and 0 swaps. Okay, in the next step you have 23, 24, which will be our key, and you will check it with you'll check it, the conditionality between 23 and 24, right? And there'll be no swaps, right? And in the next step you will have 9, 14, 23, 24, 51. You will have 51 as the key. You check it with, so there will be a condition checking between 51 and 24 and 0 swaps. So basically you had, so let me calculate the total number of operations. So for a 5 element array, my operations is actually 4. For an array of 5 elements, the operation is, total number of operations was 4. For an n element array, it will be n minus 1, right, which is basically order of n. So best case time complexity for the insertion sort is order of n, and worst case time complexity is order of n square. Is that clear? I hope that is clear. Otherwise you can just come back and revisit this. So that is everything that I had for you for this tutorial session. If there is any doubts, you can go ahead and ask. Otherwise we can close the session here. Okay. Okay, if there are no doubts, then let's close the session here. Thank you everyone for joining. So we'll meet next Tuesday at the same time, 7 to 9 p.m. Thank you.